We are the work group of Professor Volz at the Philipps University of Marburg. We are part of the characterization platform and we receive samples like these from our partners within the platform and other members of FestBatt. Today we are going to show you our workflow to investigate these battery materials with transmission electron microscopy. So let's go! First of all, we got new samples.
Here we put the air-sensitive sample inside the iron glove box and place them inside this shuttle to be able to work with plasma FIV without air exposure.
This is our plasma-focused ion beam machine. This uses an electron beam to investigate sample batteries in the micrometer range, and we can use an ion beam to create cross-sections of the battery materials. So there we can, for example, use autoslice view, where the ion beam cuts off slices of the battery material and the electron beam takes an image. And by that we can have three-dimensional investigations of battery composites, for example. If investigation at higher magnification is necessary, we can also use this machine to prepare samples for further investigation in the transmission electron microscope. For that, we chunk out some battery material and attach it to a 3mm wide 10 grid. On that, we can thin down the sample to less than 100 nanometers so that it is electron transparent. Very sensitive samples like lithium or uridite need also cryogenic conditions while thinning. For that, we have a special stage which we can cool down to approximately -190 degrees C with liquid nitrogen. Once sample preparation is finished at the plasma fit, we retract the sample into the transfer shuttle and bring this one under inert gas atmosphere to the glove box. There we can mount it into the specific temp program.
So now we want to measure the sample in the TEF. So in order to do that, we use the memory folder. It has enough gas transfer capabilities so that we can transfer the sample to the TEF without exposing it to the air. Here's the sample.
Thanks a lot. So this is our aberration-corrected scanning transmission electron microscope. This is kind of our workhorse for our atomic resolution analysis. What we do is we have a focus probe by which we can image the atoms at the atomic resolution, and we came up with a technique to also image the lithium ions. This microscope is also equipped with the EDS system by which we can check, for example, the chemical composition of the coatings on our particles. And we can, in addition to all this stuff, we can do all the analysis for the beam sensitive samples at the cryo temperature with our cryo holder.
Another method we use for investigating the battery samples is scanning precession electron diffraction here on this microscope in the back. There we go with a parallel beam on the sample. This parallel beam is processed on the sample to get high quality diffraction data, which then can be later to be used to determine phases and orientation in the sample, which for example helps for NCM samples to see if you have a rock salt or a layered structure and get the ratios of layered and rock salt structure in the sample.
Furthermore, we have specialized holders for in situ experiments for heating an atmosphere, electrical biasing, or experiments in liquid cell. For example, in this experiment, we heated a cathode particle in oxygen atmosphere and observed the structural changes.
As you can see here, a new building is being constructed to house a brand new and powerful transmission electron microscope, enabling us to conduct more advanced experiments and more precise measurements.
Hi Thomas.
Hey,
Here's the data.
perfect, thanks. I will send them off right away. We hope you got a good impression on how we prepare, measure and investigate our samples from the micro to the nanoscale. Thanks for watching.